So the topic of this presentation is mountain building in the geologic past. And so to talk about this, we're first going to start with mountain building in general. I'm sure you remember the James Hutton quote, "The present is the key to the past." This basically means that by observing today's geologic processes, we can learn more about how the Earth formed and how it changes over time because those processes are still the same today. This also applies to the process of mountain building. The way that it's going about it today is the same as the way it was formed years ago. Mountain building is called orogenesis. This is essentially the process of mountain building. And orogenesis involves many smaller processes, but the most common one of these is orogeny, which is the formation of mountains through compressional force, which I'm sure you remember learning about. This is an image of the type of mountain building that we're very familiar with as continental crust collides and mountains form from the folding of the crust. It can be difficult to get exact information of ancient mountain building when this happens because if it doesn't involve two pieces of continental crust, then some of the rock record can be destroyed because the oceanic crust that's involved can be subducted and it's not always accessible to get clues from. So in order to talk about mountain building, especially mountain building in the past, we need to first discuss the contributions of John Tuzo Wilson. Wilson was a Canadian geologist and physicist who proposed hotspots and transform boundaries, and this helped the theory of plate tectonics to gain more traction because the existence of hotspots and transform boundaries answered some questions that seafloor spreading wasn't able to account for, like why do we have random volcanic islands forming when there isn't any active plate boundary near there? But the idea of hotspots could answer that. So in 1966, he published a paper called "Did the Atlantic Close and Then Reopen?", in which he discusses possible theories or evidence for the idea that there was an ancient ocean where today's current Atlantic Ocean is that caused or resulted in the formation of the Appalachian Caledonian mountain range when it closed. So the reason why this idea exists in the first place is because the Atlantic Ocean is about only 200 million years old. It began to form with the breakup of Pangaea, which was around 200 million years ago. However, the Appalachian Caledonian Mountains, which are here, they span North America and parts of the UK and Scandinavia. They are several hundred million years older. So obviously they cannot have been formed by collisions when the Atlantic Ocean was forming because it's not possible. There's so many hundreds of millions of years in between that it couldn't have happened. So Wilson proposed, or Wilson's evidence led to the generally accepted idea that there was an ancient ocean in between the continents of North America and Europe, where today's Atlantic Ocean is, that closed. This collision created the Appalachian Caledonian mountain ranges, and then it opened up again to create what is today the Appalachian, or not, excuse me, to create the Atlantic Ocean. And this cycle of opening and closing mountains is known as the Wilson cycle. So at its most detailed, the Wilson cycle has 9 stages. So I'm going to go through them as a brief overview with each one. Stage A is the creation of a stable continental craton, which is the starting point. A craton is a portion of the lithosphere that has undergone many cycles of tectonic activity but has not been destroyed, usually because it's in the middle of continental crust and isn't on the margins, and so isn't going to be involved in plate tectonics usually. That's not always the case. It's often big, flat, bordered by oceans, and eroded to be just above sea level. And you can see in this picture, this is the craton, while this is the rest of the continental crust. So basically it's a large part of continental crust. So then we get into stage B, which is hotspot and rifting. Like most hotspots, it is created in continental crust when a mantle plume rises from the mantle and creates a hotspot. As you can see in this picture, this is the mantle plume rising and causing rifting. The heat causes expansion and cracking of the crust, and eventually it will begin to rift. There's often volcanic activity involved. Usually this would mean that the magma is mafic, but it can occasionally be felsic as well, as the heat from the mantle plume melts the bottom of the continental crust and makes the magma's concentration a little bit more felsic. So then stage C is creation of new oceanic crust, early divergent margin, and that sounds a lot more complicated than it is. Basically what it means is that the rifting continues and the continent breaks apart more. Because of the hotspot and the magma coming up from the mantle, igneous rock will fill the space left in the continent by the rifting, and because it's denser, it sinks and forms the oceanic basin. So the edges of the continent along the rifts will cool and drop below the sea level, and water fills in the rift and the basin. Stage D is full divergent margin. So you can kind of see this here. It's a mid-ocean ridge forms as the heat moves in a process of convection. So the crust cools and sinks as it moves away from its heat source. And basically what that means is that, as you can see here, where the crust just above the ridge is higher because it's being lifted by the heat, whereas as it moves away from the ridge, it sinks a little bit lower. So after about 110 million years, the crust has cooled completely, and it rests about 14 kilometers below sea level, whereas when it's at the ridge, it's usually only about 4 kilometers below sea level. So this will create ocean basins in between continents, or a full divergent margin. Stage E moves into creating a convergent boundary, a volcanic island arc mountain building. So divergence can last for hundreds of millions of years, but eventually the continents will reach the limit of the length that they can move away from each other, and they will start to move together again. This forms a subduction zone in the oceanic crust. And as a trench forms, part of the crust being subducted will heat, rise, and form a volcanic island arc as it goes over into the plate that it's subducting underneath. And you can see this in the picture here, as the plate being subducted sinks, melts from the heat, and the magma rises and forms an island arc. Stage F is island arc continent collision mountain building. And this basically means that mountains are being built as the volcanic island arc eventually collides with the continent. Subduction has continued enough that the island arc has been brought over to the continent. They collide and form mountains, as you can see in this image here. Some parts of the oceanic crust can be preserved in these mountains, and eventually the volcanic activity will stop, and when it stops, erosion begins, because as it's no longer being built, the elements will start to take away what's there at a process faster than what's being built. Stage G is Cordilleran mountain building. A cordillera is a long chain of mountains, and in this case it really just refers to a volcanic island arc. Basically what this means is the first subduction zone is now inactive because it's collided with the continent, and so it's moved away from its heat source. However, because the two continents are still converging, another subduction zone will form. And you can see this one here, where the two continents, or the continent and the earlier volcanic island arc, have collided over on the left, but there's another one forming off to the right. This starts the process of subduction of oceanic crust all over again. So stage H is continent-continent collision mountain building. Basically, this means that the remains of the ocean basin have closed and the two continents collide because all of the ocean basin has been subducted. This builds even more mountains. Over time, the mountains begin to erode. Of course, this takes hundreds of millions of years. This brings us to stage I, which is stable continental craton. A new craton is created after erosion has weathered the mountains down until the topography is nearly flat. And this brings us full circle, as this is a cycle, and we go back to where we started. So that is the Wilson cycle, but on a larger scale, it can even apply to entire continents, called the supercontinent cycle. This is an image that shows the formation and breakup of Pangaea, how it was a single supercontinent, and then over time it has moved to the continents have moved to positions that we recognize today. So supercontinents form most likely due to the trapping of heat, because large blocks of continental crust don't really conduct heat very well. Heat from the mantle will kind of pool beneath them, and this causes, again, like a very large hotspot. Heat will accumulate under the continental crust, causing it to expand, rift, and break. The oceans where today's Atlantic Ocean is have been opened and closed many times. There's evidence to suggest that. However, there is no evidence to suggest that the same is true for the Pacific Ocean, which would imply that the Atlantic Ocean is an interior ocean, meaning that as supercontinents form and break up, the ocean, or the previous oceans that are where the Atlantic Ocean is today, have been opened and closed many times as continents move together. However, the ocean where the Pacific Ocean is one that surrounds the entire supercontinent. The continents today are still moving apart after the breakup of Pangaea, but eventually they will reach the position where they will not move apart anymore and they will begin to converge again. So what does this all mean? This is just another picture of the supercontinent cycle over time. This is an example of how continents diverge over hundreds of millions of years and then come back together. So the supercontinent cycle can help explain major changes in sea level, mountain building activity, glaciation, and even the biosphere. Sea level tends to be lower when a supercontinent exists, because when it's being created, or when continents are diverging and oceanic crust is being created, it tends to be less dense, and so it's higher up and less water can sit on top of it. So when there is a supercontinent, the ocean crust tends to be older and more water will sit on it. Large portions of exposed continent can lead to global cooling, and this is because when there are large portions of exposed continent, there tends to be a lot of silicate weathering, or weathering of silicates, and when these silicates get into the ocean, they can react with dissolved carbon dioxide in the water to form solid precipitates, and now the water needs to replenish the dissolved carbon dioxide, so it pulls it from the atmosphere. Atmospheric carbon dioxide traps heat from the sun in a process called it's known as the greenhouse effect. And when there's less atmospheric carbon dioxide, this can lead to cooling on a global level. The supercontinent cycle can even relate to glaciation, because continents near the poles, such as Antarctica, experience large glaciers, which pulls water from the ocean and lowers sea level. So as you can see, the Wilson cycle and the supercontinent cycle are both very important to large geologic processes, or these processes on a global scale, and they can apply to so much more than mountain building. Thank you for your time.